Welcome to Inceptus. Today, we're building an AI agent for systems integration, focusing on automated structure mapping. One of the most time-consuming tasks in systems integration is mapping data structures between applications. Traditionally, someone has to analyze both structures, identify corresponding fields, and prepare the mapping manually. Now, imagine an AI agent doing this work automatically. In this video, I'll show how I built an AI-powered structure mapping solution using n8n Ollama and a local large language model. We'll start with the simplest possible implementation, a single AI agent that receives source and target structures and generates mappings automatically. First, I create a new chat-based workflow. The first component is the chat trigger node, which allows the user to provide a source structure directly through the chat interface. Next, I add an AI agent node. This will be responsible for analyzing the source structure and generating the mapping. Inside the AI agent, I define a prompt that describes the target structure and asks the model to find the most appropriate target field for every source field. The instruction is intentionally simple. To run the language model locally, I'm using Ollama. It provides the runtime environment for serving and managing AI models without relying on external AI services. The model itself is Qwen3:8b, running entirely on my local machine. Finally, I set the output format to JSON, which instructs the model to return valid JSON instead of free-form text, making the output easier to process in subsequent workflow steps. The sample model analyzes both structures and generates the proposed mappings. This demonstrates the key advantage of large language models. Instead of relying on exact field names, they can infer relationships based on semantic understanding. At this point, it looks like the problem has been solved. However, there is an important limitation. The model returns the result as text. Although the output looks like JSON, it is still treated as a string. For further processing inside the workflow, we would prefer to work with a JSON object rather than plain text. At this point, the output schema is embedded directly in the prompt. This makes the prompt longer and mixes business instructions with formatting requirements. To improve the design, we move the output schema from the prompt into a dedicated parser configuration. To achieve this, we add a structured output parser and define the expected output schema. The parser instructs the model to return a structured object instead of free-form text. The prompt can now focus entirely on the mapping task, while the parser becomes responsible for validating the output structure. As a result, the response is returned as a structured JSON object that can be processed directly by subsequent workflow steps. As we can see, the model correctly identifies that customer name corresponds to the buyer's full name and that customer email corresponds to the buyer's email address. What's particularly interesting is that none of the field names are identical. The model is not performing a simple text comparison. Instead, it uses semantic understanding to determine the business meaning of each field and find the most appropriate match in the target structure. So far, our target structure has been embedded directly inside the prompt. For small examples, this approach works well and keeps the workflow simple. However, real integration projects are very different. Target structures often contain hundreds of fields, multiple nested objects, and complex hierarchies. Embedding such structures directly into every prompt quickly becomes inefficient, difficult to maintain, and expensive in terms of token consumption. A more scalable approach is to separate the target structure from the prompt itself. Instead of providing the structure directly, we expose it through a dedicated tool. The AI agent can then retrieve the target structure only when it is needed. From an architectural perspective, this is a significant improvement. The prompt becomes smaller, the target schema can be maintained independently, and the agent gains access to external information through tools. At least, that's the theory. In practice, introducing tools creates a completely new class of challenges. As we'll see in the next examples, getting an AI agent to use tools reliably is often much harder than simply writing a good prompt. At this point, we want to move beyond a static prompt. Instead of embedding the target structure directly inside the prompt, we expose it through a dedicated tool. The agent is instructed to call the target_schema tool before generating any mappings. However, this introduces a new challenge. Even though the prompt explicitly requires the tool to be called, language models do not always follow such instructions. Tool usage remains a decision made by the model itself. As a result, the model may attempt to generate a response without retrieving the target structure first. The next challenge concerns the language model itself. Initially, I selected a model that did not support reasoning or thinking mode. At first, this seemed perfectly acceptable. The model was able to answer prompts and generate mappings. However, once tools were introduced into the workflow, its limitations quickly became apparent. Our goal was straightforward. Instead of embedding the target structure directly inside the prompt, we exposed it through a dedicated tool. The agent was instructed to call the target_schema tool before generating any mappings. At first glance, this seems simple. We provide a tool, explain its purpose, and explicitly tell the model to use it. In practice, however, tool usage is still a decision made by the language model. Without reasoning enabled, the model often follows a much simpler execution path. It receives a prompt and immediately attempts to generate an answer. As a result, it may completely ignore available tools and rely only on its internal knowledge. What's particularly interesting is that the generated output may still look correct. In our example, the model produced mappings that matched the expected target structure, even though the tool was never called. This happened because the target structure was relatively simple, and the model was able to infer it from common business concepts such as customer name, full name, and email address. At first sight, everything appeared to work correctly. The generated mappings looked valid and the problem was not immediately visible. However, the model was not using the actual target structure provided by the system. Instead, it generated a target structure based on its own assumptions and prior knowledge. The error message was highly misleading. n8n reported that the model output did not match the required format. Naturally, the first suspects were the output schema, the parser configuration, or the tool definition. After reviewing all these components, we discovered that none of them were responsible for the failure. The actual problem was the selected language model. It did not support reasoning or thinking mode, which was required for reliable tool usage. In other words, the symptom appeared to be a formatting issue, while the root cause was a model capability issue. Once we switched to a reasoning-enabled model, the workflow started working correctly without changing the schema, the parser, or the tool definition. When the tool is called successfully, we can clearly observe the agent execution flow. The language model first evaluates the request. It then invokes the code tool to obtain the target structure. After receiving the tool response, the model continues its reasoning process and generates the final mapping. This sequence is one of the key characteristics that differentiates an AI agent from a simple prompt response interaction. The model is no longer limited to the information contained in the prompt. It can actively retrieve additional information when needed. Let's summarize what we've learned. We started with the simplest possible solution, a single AI agent receiving source and target structures and generating mappings automatically. For small examples, the results were surprisingly good. The model was able to identify relationships between fields based on semantic meaning rather than exact field names. Next, we improved the solution by introducing a structured output parser. This allowed us to transform the response from plain text into a structured JSON object that could be processed directly by subsequent workflow steps. However, as the solution evolved, we encountered a fundamental scalability problem. Real integration projects contain large and complex structures that should not be embedded directly into prompts. To address this, we moved the target structure into a dedicated tool and allowed the AI agent to retrieve it when needed. This seemingly simple architectural improvement revealed several important challenges. We discovered that tool usage cannot be taken for granted. The model may ignore a tool even when explicitly instructed to use it. We also learned that reasoning capabilities are critical for reliable tool execution. Without thinking support, the model may generate outputs that appear correct while relying entirely on assumptions instead of actual system data. Perhaps the most important lesson was that symptoms and root causes are not always the same. An error reported as a formatting problem turned out to be a model capability problem. Only after switching to a reasoning-enabled model were we able to achieve reliable tool execution. At this point, we have moved far beyond a simple prompt-based solution. We now have an AI agent capable of retrieving external information, reasoning about its actions, and generating mappings based on actual target structures rather than assumptions. And this leads to the most important conclusion of the entire project. AI is extremely effective at understanding business meaning and identifying semantic relationships between fields. However, AI should not be responsible for everything. The most reliable solutions combine AI capabilities with deterministic algorithms, validation mechanisms, and well-designed workflows. In other words, the goal is not to replace algorithms with AI. The goal is to use AI where it adds value and use algorithms where predictability and reliability matter most. That's exactly the architecture we'll continue to build in the next stages of this project.